I will start with a new concept of electrostatic field energy. And so far, in previous chapters, we have defined some quantities which is related to the energy. And one of them was the potential. And if you multiply the potential difference of 2 points by charge Q, you find the potential energy difference of any charge from going from one point to another. So we have defined electrostatic potential energies of point charges. But the question is, what if in some region of space you don't have any charges but field, the electric field? How do you then express the energy of that region in terms of the electric field? So I will start by creating this uniform electric field between two charge planes. Remember, we have seen these two charge planes, uniformly charged planes. One is Q, the other is minus Q. And between two plates, which has a distance h, the electric field is just a constant, the charge density sigma divided by epsilon 0, right? You remember this, you have calculated this before by using Gauss's law. And what if I move one of the plates in the upper direction a distance x, right? What happens? Do I have to do work for this? Suppose this configuration is in outer space, there is no gravity, nothing, and you just move one of the plates a distance x away from the other one, then do you have to do some work?
Yes.
So what you do, in fact, before I answer this, in fact, you create an additional electric field, this additional space, x times h, whatever, right? Previously, this space of this region of the space previously had no electric field, but you have just created a new electric field at that point, right? So if I can express the energy I spent to move this plane to a new configuration, then this energy should be expressed in terms of the electric field of this region, right? So this is the idea, that how can I relate the electric field by energy, right? If you do this, you enlarge the space, the volume between two planes, you don't change the strength of the electric field. The electric field strength is the same, sigma divided by epsilon 0, because there is no any distance expression on the electric field, right? It's just a constant. It's a constant, same electric field. But you create an additional electric field in an additional space, in an additional region of space. So let's then first express the work I have to do this movement of the plane. So I have to move this plane by applying a force, right? I have to express this force in terms of the electrostatic forces between these two planes, because planes are oppositely charged and they are attracting each other, right? If I move them, one of them, away from each other, and I have to overcome the force, electrostatic attraction force between them. So if I move this a distance x, then the work done is not zero. The force applied by me times the x is the total work done, right? And this force is constant because the electric field is not changing, right? If you have a charge Q in some region of space, and this region of space has a constant electric field, then this charge will feel a constant electric force all the time. So the force is constant. What about the force in terms of this field, electrostatic field? If you look at very carefully the one of the plates, okay, let's pick up these positively charged plates. This plate is a metal plate, and it has no zero thickness. It has some finite thickness, right? In macroscopic picture, It has some thickness. It's like a slab of metal, right? It has thickness. But we know that the charge is always on the surface of a metal, right? If it has a finite thickness, then the charge, this plus charge, must be on its down surface, right? And this is extra charge, by the way. So there is no charge, nothing on the upper surface. And I know that the electric field inside this slab of metal is equal to 0, right? Because inside any metal in electrostatic, the electric field is always 0, no exception. Okay? The electric field inside metals is always 0. So the electric field is 0 in this side. You can see that, right? Okay. Oradakiler görüyor mu tahtayı? İyi. Gerçi bu tarafa da bakmıyorlar ya. Bazen küçük yazıyorum da. So the electric field on one side of this charge distribution, on the top of this charge distribution is 0, but on the bottom of this charge distribution, the surface charge distribution, the electric field is non-zero. It's sigma divided by epsilon 0. So if I move a charge inside an electric field, and I will feel electrostatic force, just the charge times the electric field. But the thing in here, that this charge, only one face sees the electric field, other face do not see any non-zero electric field. Electric field is 0 on the other side. If this charge, Q, were completely inside an electric field on the bottom part and the upper part has the same electric field, then I would say that the electric force on this charge will be just Q times the electric field, Q times E, electric field. But since only one side sees the electric field and other side there is no electric field, then I can say that the force of this charge Q, the total charge Q, experiences just half of Q times E. Is that a logical reasoning for you? If yes, okay. And so by reasoning, I can say that the force, at least I have to apply, is just the charge Q times this electric field E, which is sigma divided by epsilon 0, divided by 2. So I apply this force, a distance x, because I move the plane, a distance x, then the total work I can find by multiplying this force times x, and the force is Q times E divided by 2 times x. So let's do this. So the force is not equal to Q times E, but it is equal to Q times E divided by 2, because the face, only one face sees the electric field. The other face is just, there is no electric field. And of course the total work is just one half Q times E times x. So the work required to create an additional electric field in that region of space, or the energy required to create this additional electric field in that space, a volume x times A. A is the surface area of the plate, right? So inside a volume, I create an electric field, which has sigma divided by epsilon 0 strength. Then the energy I have to spend for this is this quantity. Well, can I express this work just in terms of electric field strength? Not charge Q, but electric field strength. So how can I express this Q in terms of electric field? Well, this charge Q and sigma has a relation between them. Q is equal to sigma times A. And I know that sigma is also equal to the strength of the electric field times epsilon 0. So I can express this Q in terms of electric field, right? And in terms of electric field, this Q is sigma times A divided by epsilon 0, right? Sorry. Instead of Q, I can write down sigma times A, because the sigma is the surface charge density. If I multiply this by area, I have the charge. And in addition, I multiply this expression by epsilon 0 and divide by epsilon 0. Nothing changed, right? But I know that sigma divided by epsilon 0 is E. So I can replace this by E, and we have one more additional E inside. So at the end we have this 1/2 epsilon 0 E squared times A, the area of one of the plates, times X, where X is the distance that I move this upper plate. So if you see this A times X as the volume, because A is the area of the plate and X is the height, the X times area, then the volume of the region space that I created electric field, right? So this work divided by the volume can be expressed in terms of only electric field. E squared divided by 2 times epsilon 0. So I can, in fact, divide this work by the volume to find the energy density of this electric field. And this is just this quantity, 1/2 epsilon 0 E squared is the energy, or joules, per unit volume, or meter cube, which is inside this region of space where we have a non-zero electric field, which is equal to sigma divided by epsilon 0. So if you only look at a region of space, and if this region of space has some electric field, then it has energy. Okay? Any region of space which has non-zero electric field has electrostatic energy. Apart from any charges or nothing, if you have electric field in some region of space, then you can easily express the electrostatic energy just in terms of the strength of the electric field. All right, so since this is the energy density per unit volume, to find the total energy of any region of space which has some electric field which is also not constant, even the electric field is not constant in some region of space, you can calculate the total energy of that region of space by taking this integration. Okay, because the energy density is just this 1/2 epsilon 0 E squared, and if you multiply this by volume and take the integral of the region or of the space that you are interested, you will find the total electrostatic energy at that volume. Now, let me define what the capacitance is. So the capacitance is defined by this ratio. The capacitance of a metal object. First of all, I have to clarify that the capacitance is only defined for metals. There is no capacitance for insulators. Okay? This is definition. And the capacitance of any metal object is defined, this is definition, by its total charge divided by its potential. V, here you see, is the potential of this metal. For example, if you have a metal sphere and have a charge Q, then what is the potential of a metal sphere? If it is a radius R, then it's K times Q divided by R, right? Its total charge is Q, and its potential is K times Q divided by R. If you divide this Q and V, then you will obtain some new physical quantity which we call the capacitance. Okay? So this new physical quantity has, of course, its own unit, and since Q is in Coulomb and V is in volt in SI unit system, we call this special ratio, Coulomb divided by volt, as farad. It is the unit of capacitance. Let me calculate then the capacitance of a charged sphere. What is the capacitance of a charged sphere? Again, if it has a charge Q and it is radius R, whether this sphere is a solid sphere or a shell doesn't matter, because the shell and the sphere, solid sphere, has both the same potential, right? Whether it's inside is full or empty, doesn't matter. The potential is only depends on the radius and the charge Q. So its potential is Q divided by 4 pi epsilon 0 R. This 1 over 4 pi epsilon 0 is just K, the Coulomb constant. And let's calculate then this ratio Q divided by V. And V is already in terms of Q. And you will see that the capacitance is nothing but 4 pi epsilon 0 times R. The capacitance of a metal sphere is just 4 pi epsilon 0 times its radius. Okay. What does this mean? The capacitance, first of all, if you look at it, grows with the radius. If you have a larger radius metal sphere, you have a larger capacitance. Capacitance means the capacity of holding charge. Okay? If you have a larger object, it has the larger capacity of holding more charges, right? If you have a small charge, it will collect less charges, of course. Because if you connect to a potential that we have considered in previous lecture, two different radius spheres, right? Remember, they were at both same potential, but the smaller sphere holding a less charge, and the larger sphere holding a larger charge. Q2 was always larger than Q1. That's something related with the capacitance. Because the larger sphere has a larger capacitance, that means it holds a larger charge. So that's it, one thing. See, the C grows with R. As you enlarge the sphere, then you have more capacitance. What about the Earth? Well, the Earth is not a conductor, but again, if you think that the Earth's surface has some conducting material, you can calculate the capacitance of Earth. So in terms of its radius is 6,400 kilometers. Let's calculate the capacitance of a metal sphere in the size of Earth, and that means 700 microfarad. See, an object as large as Earth, a very big object, it has 700 microfarad. Micron is 10 to the minus 6. So 1 farad is very, very large quantity in terms of capacitance. Okay? Just to appreciate the value. And when you look at these capacitors that you can see anywhere, in fact, we have some capacitors in our lab, just you already have seen small cylindrical things beside the resistors. Poşetlerin içerisinde gördünüz geçen labda. Küçük silindir şeyler vardı. Onlar rezistansların yanında resistörlerin. Onlar kapasitör. Onların üstüne bakarsanız microfarad, böyle milifarad falan yazar. Yani çok büyük değil. So 1 farad of capacitance requires a size of sphere radius having 9 times 10 to the 9 meters. 10 to 9 makes almost 10 to 10. It is 1 million meters, right? Huge. It's almost 6 orders of magnitude larger than the size of Earth. It's a huge quantity. So 1 farad is huge number. That means 1 farad of capacitance can hold very, very large charges. The next is the previous one was the capacitance for only one object, but we usually have the capacitors that we use in our electrical circuits. It's composed of two conductors, not only one conductor, but we have as the capacitors as two conductors which have some distance d with respect to each other. We have one conductor A which has positive charge, and the other conductor B we call which has negative charge. And you keep the distance fixed between them, and you keep their potential difference also fixed. With this charge, if two conductors have a potential difference between them, okay, then one of the conductors is positively charged and the other is negatively charged. Okay? Or let me say more precisely, these two conductors must have different charges. Okay? But we define the capacitance of two conductors, two conducting system, if they hold a charge Q. If one of them has hold charge Q, the other must hold a charge minus Q. Okay? This is definition. A capacitor of two conductors is defined by one of the charges of the conductor, and this charge is the same for both conductors, but they are opposite in sign. If you define the capacitance of a conductor, two conductors, then one of the conductors has positively charged Q, the other has exactly the same magnitude but opposite charge, minus Q. If they have, for example, plus Q minus 2Q, you cannot define any capacitance. Forget it. Okay? There is no such thing. We have a capacitor of two conductors. One has a different charge. Well, one has a charge in strength different than the other one. They must have the same strength of charge, and their sign must be opposite. This is always must. And if you keep these two metals having a potential difference, of course they have different charges, so they must have different potential. If they have different charges in sign, they must have different potential. So we redefine the capacitance of two charges as the charge of one of the capacitor, Q, not the total charge. Well, if you look at the total charge is 0. Plus Q minus Q is 0. Just on the denominator, we have the charge, the strength of the charge of the one of the capacitors, Q, divided by the potential difference between them. This is the definition of the capacitance of two metal objects. Okay? It is similar to the definition of the capacitor of a single one metal object. It's again Q times Q divided by the volume. But this time the potential difference is the potential difference between two pieces of the conductor. Okay? This conductor may have an absolute potential, some potential, and this conductor has some other absolute potential, but we don't care their absolute potential, their potential difference we care. All right. Let me calculate an example of a capacitor of parallel plate capacitor. In parallel plate capacitor, we have two plates. One is positively charged and the other is negatively charged, and they both have the same area. They are metals. They are two-dimensional surfaces. They keep a distance d between them. You have to keep the distance the same between them. And let's calculate the capacitance of this object. So, of course, they have the electric field, non-zero electric field between them. It is sigma divided by epsilon 0. And to find the potential difference between the two plates, because we need a potential difference between these two conductors, you can use this formula, the potential difference, the line integral E dot dr, because we already know what the E inside the between these two plates. From this, you can easily calculate the potential difference as E times D. D is the distance between the plates, okay, and the electric field is sigma divided by epsilon 0. So this is the potential difference, E times D. And the charge is sigma times A, right? If you apply this formula to find the capacitance, you will find sigma A divided by ED, and E can be replaced by sigma divided by epsilon 0, so that we can get rid of these two sigmas in denominator and denominator. So you have A, one of the surface area of these plates, times epsilon 0, a physical quantity, it is constant, divided by the distance between the plates. So when you have two plates, metal plates of size A area, and you keep the distance d, the capacitance grows with the size of the surface area. Of course, this is very intuitive, very logical, because if you enlarge the surface area, then the capacity to hold more charges is more, right? you get more charges with a larger surface area. So the capacitance is, you see, proportional to A. But it is inversely proportional with the distance between them of these two two plates. If you keep the distance smaller, if you bring these two plates closer to each other, they have more capability of charges. Okay, you can put more charges if you bring them closer. If you make them far apart, it is more difficult to put more charges on the plates. So this is so. It depends inversely proportional on the distance between them. Okay. All right. An example: if you have, for example, 25 meter one side, let's say aluminum folio, it's a metal, and it has one side 5 centimeters, two aluminum folio on top of each other. If you keep the distance between them 0.01 millimeters, then you can reach the capacitance of 1 microfarad. Well, this is approximate, I think. Okay, so 1 microfarad, you can have, you must have 25 meters aluminum plates. What you see these cylindrical capacitors in the lab, in fact, they are folded aluminum folios. And in between two folios, they have a paper as insulator, because they shouldn't touch each other. If they touch each other, they discharge, right? So they put a paper in between two aluminum folios and roll them up. And you put this into a cage, which is cylindrical. You form a capacitor. So let's talk about the energy stored in a capacitor, because initially, if you have two parallel plate capacitors, if there is no charge, since there is no electric field, no charge, no electrostatic energy. But as you charge these plates, one is minus, the other is plus, you start creating electric field between them, right? And when you start charging a capacitor, you start storing electrostatic energy between them. Well, so let's think about it. Well, you already know that if there are 2 points, A and B, and one is at potential VA and the other is potential VB, if you move a charge from point A to B, then you have to spend energy which is equal to Q, the charge Q, times VB minus VA, right? This is the electrostatic energy. And this is the work to do to move a point charge from one point to other. If these points are at different potentials, then the potential difference multiplied by the charge itself is the work to do to move this point charge from one point to another. So suppose you have two plates, okay, and initially they are neutral. There is no charge, but one by one you bring some extra charge, plus charge, from the lower plate to the upper plate. Suppose you pick up one positive charge and you move to the upper plate. Initially there were no electric field, but since now you have this different charge on the different plates, you created a potential difference and you created electric field. As long as there is an electric field between two regions of space, and the endpoints will have a potential difference, because the line integral is non-zero, since you have a non-zero electric field. As you continue to bring more charges from the lower plate to the upper plate, you will create more electric field, you will create more potential difference, right? And you continue this to have a maximum charge on the upper plate, plus charge, and the minus charge on the lower plate. And you have just created some electric field and the potential difference between 2 points. Let's imagine how much work you have to do to move dq charge from the lower plate to the upper plate. If the plates had already a potential difference delta V, then just like here, to move an extra charge from one plate to other plate, you have to consume a work of dq times delta V. Because remember, to move a charge from one potential to other potential, what you do is you do a work which is equal to the charge q times delta V. So you do the same here, and this will be the infinitesimal work you have to do to move a charge of dq in a potential difference delta V. But I can always express this delta V in terms of charge, right? I can express this delta V in terms of charge and the capacitance of these two plates, right? These two plates has a constant capacitance, C, and this delta V, since C is equal to Q divided by V, and this delta V can be expressed as Q divided by C. So this is the infinitesimal work to do to move an extra charge from one plate, dq, to other plate. If you sum these, right, these dWs, small works, then you will find the total work done to move a minus charge q from the lower plate, plus charge q from the lower plate to the upper plate. Let's do this. To do this, what you do is you just take the integral of this expression. dq times q divided by c, you will take the integral from 0, because initially you had no charge, to a maximum charge, which is q, and you will take this integral dq times q divided by c. Well, c is constant, and you can take this c outside the integral, and you have q times dq integral. What is the result of this integral? Q squared over 2. So, but if you put, of course, the endpoints of the integral, then you will get 1/2 the total charge q squared divided by c is the work done to move the charges, q charges, from here to here. Or this work is energy, right? This energy is the electrostatic energy you stored in this capacitor. So you can always express the electrostatic energy of a capacitor in terms of its charge q and in terms of its capacitance, C. But there is always this relation between C, Q, and V. If you want to express this energy in terms of only the potential difference and C, or if you want to express this energy in terms of C and Q, or Q and V, whatever, you have these three different expressions for the total energy. You can either express this in terms of Q and C, in that case 1/2 Q squared divided by C, or in terms of Q and V, because C, Q, and V are related by this formula, this relation, or in terms of only C and V. These are all okay, and you can express the total energy in terms of these pairs. But what about electric field? You can also express the charge density in the electric field, right? Or the charge in terms of electric field, or electric field in terms of charge. So that means you can also express this total charge stored in the capacitor in terms of the electric field between the plates. So we go back to the previous case that I have calculated the energy of any region of space which has only electric field, right? 1/2 epsilon 0 E squared. If you do this for the capacitor, then you will get this expression, the same electrostatic energy U in terms of the electric field only. 1/2 epsilon 0 E squared times the volume of the region between these two plates. Okay? So Now let's calculate the capacitance of a spherical capacitor. A spherical capacitor has two conducting shells. One has, in this picture, has a radius of A and it is positively charged, and the outer shell, the spherical shell, has a radius B and it is negatively charged. The inner shell has, let's say, a plus Q charge, and the outer shell has minus Q charge. So the first thing is we have to calculate the potential difference between these two conducting shells, and the only region that has a non-zero electric field in this configuration is the region between these two shells. This region has non-zero electric field. The outer region, the outside of outer shell, has zero electric field, because if you take any Gaussian surface around these two conductors, the net charge is inside is zero, and there is no flux, and that means the electric field must be zero outside. And similarly, the electric field inside the inner shell is again zero, because there is no any net charge if you take any Gaussian surface inside. So that we know that for a charged metal, the potential at the surface of this charged shell is just the charge Q divided by 4 pi epsilon r, epsilon 0 r, and r is the radius of the shell. And for our example, the inner shell, since the inner shell has a radius a, the inner shell is at a potential Q divided by 4 pi epsilon 0 times a. So this is the potential of the inner shell. And as you go away from the inner shell, the potential drops as 1 over r. So when you come to the inner surface of the outer shell, the potential will be equal to Q divided by 4 pi epsilon 0 a, because the radius at the outer shell is b. So this is it. And you don't need to take the line integral, because we already know how the potential changes when you go away from a spherical conductor. So the next is easy. Just we have to divide one of the charges of these shells, and we divide it by the potential difference between these conductors, and we will take just the difference of these two terms. And when you do this, we get this 4 pi epsilon 0 1 over inverse a and inverse b, the difference between the inverse radiuses. So the result is 4 pi epsilon 0, the inner radius times the outer radius, divided by the radius of the outer shell minus the radius of the inner shell. So this is the capacitance of a spherical conductor, and spherical conductors are the radii A and B. And so you see the capacitance does not depend on charge, it only depends on the radii of these two spherical conductors. And of course, the constant, physical constant epsilon 0. Now let's calculate the capacitance of a cylindrical capacitor. So the cylindrical capacitor has two conductors, coaxial conductors, cylindrical conductors. The inner one has the plus charge Q, and the outer one has the minus charge Q. Remember, for a metal capacitor, two conductor capacitor, one conductor must be positively charged, the other conductor must be negatively charged, and the strength of the charges of these two conductors must be equal to each other. So the length is given by L, and the inner core has radius of A, and the outer shell has the radius of B. So to calculate the capacitance, of course, first we have to calculate the potential difference between these two conductors, the inner core, the plus Q conductor, and the outer shell, minus Q charge. For this, we may use the direct result of a linear charge density, electric field of a linear charge density around the inner conductor. And the first thing is, we know that the electric field inside of a conductor is 0, So the electric field is 0 for the radiuses less than A, which is the radius of the inner conductor, and the electrical field is again 0 for the radiuses which are larger than B, again because of the Gauss's law. Let's think a Gaussian surface, cylindrical surface, which is which surrounds these two conductors, imaginary Gaussian surface. So the flux through this Gaussian surface will be 0 because the total charge which resides in this Gaussian surface will be equal to 0 because we have a net 0 charge inside the Gaussian surface, plus Q and minus Q. What about the electric field in between these two conductors? Again, by Gauss's law, we already calculated that for a linear charge density around the electric field around the region of the linear charge density will be equal to Q divided by 2 pi epsilon 0 r, lambda divided by 2 pi epsilon 0 r. Here, lambda is the linear charge density. In our configuration, the linear charge density is given by the total charge divided by the length of these cylinders. So this is the expression for the electric field, and it is radially outward, and this is for the radiuses between A and B. Next, we will calculate the potential difference between the plus Q and the minus Q. And we will use the definition of the line integral for this. The potential difference of the outer shell VB minus VA is equal to the minus the integral of the line integral of the electric field from A to B. We will pick up just any line connecting from the center of the conductors to the outward direction. So, of course, this dr will be dr times the unit vector r. So the integral is just a simple integration of 1 over r from A to B, and these are the constants, and Q divided by L is the linear charge density, and the result is just the total charge of one of the conductors divided by 2 pi epsilon 0 times L, which is the length of the cylinder, times the natural logarithm B divided by A. B is the radius of the outer shell, the cylindrical shell, and A is the radius of the inner core. So once we know this potential difference, the rest is very easy to calculate. The capacitance is just the total charge of one of the conductors. Again, the total charge is for both conductors is 0, but the definition of the capacitance is just take the capacitance of one of the conductors, and this is divided by the potential difference. So the potential difference is given in terms of the total charge Q, and this expression reduces to 2 pi epsilon 0 times L, the natural logarithm B divided by A. This is the capacitance of a cylindrical capacitor. Suppose we have again a parallel plate capacitor. We have two different kinds of dielectric materials in between the plates, but this time the plates are not sandwiched between the plates, but the dielectrics are side by side, and half of the region is with K1 and the other half, the right half, is K2. And suppose the total area of one of the plates is A, then half of the area has the K1 dielectric between the plates, and other half has the K2 dielectric between the other half of the plates. Well, suppose the thickness of this each dielectric is D, they are equal to each other, and we apply a potential difference between these two plates. When you look at this closely, there is no harm to separate the upper and lower plates into two halves, okay? and they are connected by a wire, because since the potential of let's say the upper plate is kept at V, then dividing and connecting these halves into each other will not make any difference of the potential which is kept at V of this upper plate. If you divide, separate one big plate into two halves and connect these two plates by a wire, then in terms of the potential, there will be no difference. They will be still kept at the same potential with the initial configuration. And of course, the lower potential will be the same. The lower potential again for both separations will be the same because they are connected by a wire. But when you look at this configuration, which is equivalent to this capacitor, is nothing but having two capacitors which are C1 and C2, which has the dielectric constants dielectrics between the plates K1 and K2, which are parallelly connected to each other. So we have instead of one big capacitor which has an area of A, we have two different capacitors which has half of the area of the previous one, and they are parallelly connected to each other. So of course, for this configuration, the potential difference between the plates for each capacitor will be the same, V, right? And we know from the connection of capacitors, parallelly connected capacitors, the equivalent capacitor is nothing but the capacitances of these each capacitors, C1 and C2, which are parallelly connected to each other. And of course, it is very easy to express these capacitances C1 and C2 in terms of the dielectric constant, the epsilon zero, the surface area of the plates, and the distance, the thickness of the capacitor. The C1 is just K1 times epsilon zero A divided by 2 divided by D, and similarly the other one has the similar expression, K2 epsilon zero A divided by 2A divided by 2 half of A divided by D. So that the explicit expression for the equivalent capacitance is nothing but epsilon zero A divided by 2D, and in parentheses the sum of their the dielectrics constants. Well, with this information, you can easily figure out the charges of these plates, okay? Well, you separate these plates into half. They are at the same potential, but do they have the same charge? Right? Of course, when you apply the relation between the charge, the capacitance, and the potential difference, you will notice that these charges, since they have a different dielectrics in between the plates, they will have different charges. For example, the first capacitor will have a charge on one of the plates as C1 times the V, the potential difference, and this is nothing but K1 epsilon 0 A divided by 2D times V, and the charge on the other capacitor, which has the dielectric constant K2 in between the plates, will have K2 epsilon 0 A divided by 2D times V. So these charge ratios will be nothing but if you express this ratio as Q1 divided by Q2, it will be nothing but equal to the K1 divided by K2. If larger the dielectric constant will have the larger charge on the plates. So this is the result, and we can safely say even these plates are at the same potential, and this does not mean necessarily they will have the same charge. In fact, if they have different materials in between the plates, then they will always have different charges on the plates. Okay. Okay, we have a parallel plate capacitor, but between the plates of a capacitor we have two different kind of dielectrics, and they are sandwiched. They are parallel on top of each other, and the one of the dielectrics has dielectric constant K1 and the other one has dielectric constant K2. The total distance between the plates of the capacitor is D, and the thicknesses of each dielectrics as D1 and D2. And if you apply a potential difference between the plates of this capacitor, for example, the upper plate has a higher potential, then we will have a positive Q of the upper plate. And let's define the area of one of these plates as A. And of course, the electric field inside these different dielectrics will be different. Let's call one of the electric field as E1, which is for the dielectrics K1, and the E2 is for the second dielectric. Remember, for a parallel plate capacitor, the electric field is just sigma divided by epsilon 0 in between the plates, and sigma is just the charge density, surface charge density of one of the plates. It's just, for example, in here, Q divided by A. Then in that case, if you put a different dielectric material, then the electric field will be modified by sigma divided by epsilon 0 times 1 over K1. So the electric field will be smaller than the electric field which is in vacuum by a factor of K1, and for the other material, the electric field will be expressed as sigma divided by K2 times epsilon 0. So the next thing is, of course, we have to, with this configuration, we have to find the total potential difference between the plates in terms of the electric fields and their thicknesses of the dielectrics. So, of course, since the potential is just a line integral between any 2 points, then the total potential difference will be E1 times D1 and plus E2 times D2. Because if you go from one point on the upper plate to the other point on the lower plate, then you will cross the first dielectric, which has distance D1, thickness T1, by multiplying its E1. You will calculate the potential drop inside this first dielectric, and E2 times D2 will be the potential drop inside the second dielectric. So the total potential difference may be expressed in terms of the thicknesses and the electric fields inside these dielectrics. But what are these electric fields? We have to be more explicit. As I said, sigma divided by K1 times epsilon 0 is the electric field inside the first dielectric. And if you multiply, of course, by D1, you will have the potential difference just between the points of this first dielectric, between the point of the upper point and the lower point. And sigma divided by K2 times epsilon 0 is the electric field inside the second dielectric. And then comes to apply this expression to the general formulation of the capacitance. And the capacitance, of course, the total charge Q divided by the total potential difference between the metal conductors. And well, let's express this equivalent capacitor as 1 over C, and you will see why I choose to express this the total capacitance as like this. And of course 1 over C will be V divided by the total charge of one of the plates, and let's express this explicitly. The total charge is just the charge density, surface charge density, times the one of the area of the plates, and this will be multiplied by this expression that we have previously written down. And if you simplify this expression, of course, you cancel out the sigma, the surface charge densities, and you will have these two terms, the addition of these two terms. One is D1 divided by K1A epsilon 0, and D2 divided by K2A epsilon 0. But if you look at closely what this expression is, A times epsilon 0 divided by D1 is nothing but the capacitance of a capacitor which has thickness D1. And if you multiply this by K1, then this capacitor having a dielectric between the plates which has dielectric constant K1. So this is just 1 over C1, and this is just 1 over C2, where in the second case we have a parallel plate capacitor which has thickness D2, and in between the plates we have the material K2, material dielectric constant, having a dielectric constant K2, and well, this is the total capacitance, equivalent capacitance is just expressed as the sum of these two inverse capacitances. Then you will see, you will recognize that this is nothing but the total equivalent capacitance of this configuration is nothing but having two capacitors which are serially connected to each other, right? So this expression is the finding the total capacitance which are serially connected to each other. Then, and this configuration acts like as if we have two different capacitors with two different thicknesses and two different dielectric materials. They are connected in series. Okay, so this is our end result. Well, if you had not two different materials, but three different materials, which are D1, D2, and D3 as the thicknesses of the materials, and they are of course sandwiched, they are parallel on top of each other, then you would have 1 over C1 plus 1 over C2 plus 1 over C3. So you will apply the same trick, and you first have to calculate the total potential difference, and this will be E1 D1 plus E2 D2 plus E3 D3, and whatever the number of dielectrics inside, which are sandwiched between the plates, then you will have a capacitance which are serially connected, as many dielectrics as you have inside between these two plates. In this example, we have two different dielectric shells, dielectric materials, thicknesses, which are in spherical distribution. And in fact, we have a metal, charged metal with plus Q, which has radius A, and around this metal we have a shell of dielectric material with dielectric constant K1, which has the radius B. And around this one we have another dielectric material which has dielectric constant K2 with the radius C. And on the outer shell we have the second metal which has the negative charge minus Q. So we have two metals, plus Q and minus Q. In between we have two different spherical dielectric materials which has K1 and K2 dielectric constants K1 and K2 at radii B and C. So what is the question is, what is the capacitance of this configuration? Okay. Well, there is nothing changes, there is no difference if you put just on the border between two dielectric materials K1 and K2 a metal shell which is very thin. Okay, you see that only the cross section of these spherical capacitor, and we put a metal shell just in between, very thin metal shell between two dielectric materials, and there will be no difference. Why? Because there will be no any potential difference between K1 and K2 right at the border. And when you put this metal shell, the inner surface will accumulate minus Q charge and the outer surface will accumulate plus Q charge because of the electric field between K1 inside the K1 and K2. Okay, so once we do this, what we have in that case, we have two spherical capacitors which are serially connected to each other. Okay, so that means you will apply the rule of finding the equivalence capacitor of two serially connected capacitances, and each capacitance is a spherical capacitor, and we know already what the expression is for a spherical capacitor which has plus charge Q minus charge Q as the metal shells, and the capacitance expression for a spherical capacitor is nothing but 4 pi epsilon 0, the radius of the inner shell, metal shell, and the radius of the outer shell, and this multiplied and divided by the difference between these radii. And if there is, of course, between the plates, there is no any dielectric material, which we have only vacuum or air as the insulator between the plates. But of course, if you have a dielectric material, then you will multiply this expression by the dielectric constant. So the inner capacitor, the inner spherical capacitor, in that case C1, that we call C1 as K1 times 4 pi epsilon 0 A times B divided by B minus A, and the outer spherical capacitor, which is the capacitance between this plus Q plate and the minus Q plate, and we will have that in that case K2 times 4 pi epsilon 0 B times C divided by C minus B. So the equivalent capacitor is just, we will add these capacitances serially, and the expression for C is just C1 times C2 divided by C1 plus C2. And if you simplify this expression with this formulation, then you will get the end result as 4 pi epsilon 0 A times B times C divided by this expression K1A C minus B plus K2C B minus A. And for verifying this formula, if you put K1 and K2 is equal to 1, that means you will have only one capacitor, spherical capacitor, and the inner radius is A and the outer radius is C, then of course you will have the net capacitance as 4 pi epsilon 0 A times C divided by C minus A. But will we have this if you put K1 and K2 is equal to 1? When if you put K1 and K2 is equal to 1, you can simply check, it's just an algebra, then C would reduce to this expression. 4 pi epsilon 0 A times C divided by C minus A. So this expression is verified, and if we have two different dielectric materials in between two spherical conductors which are in the shape of a sphere, then you will have a capacitor, serially connected capacitor, and each capacitor will be given by the capacitance of a spherical capacitor, this expression, and the end result is just you add these capacitances serially to get the final equivalent capacitance. We have a parallel plate capacitor with air gap between the plates, and the charge densities are sigma plus and sigma minus with the area A, and the distance between the plates is given by D. So we know that the capacitance is given by this simple expression epsilon 0 times the area of one of the plates divided by the distance between the plates. So the question is, what happens if we insert a metal slab in between these two plates with a thickness A? So this is a metal, and as soon as we put the metal inside, and because of the electric field between the plates, this metal slab will have induced charge densities on each faces facing the upper plate and lower plate, and the charges will distribute themselves. Well, by the way, initially this slab has no net charge. Even we put the slab in between, there is still no charge. The total charge is equal to 0, but because of the electric field, there will be induced charge densities on the surfaces. So the upper surface will have minus charge density and the lower surface will have plus charge density in order to make the electric field inside the metal slab 0. So this is needed. We know that every metal has 0 electric field inside, so to provide this, the charges must distribute it on the slab like this. Okay, so what happens to the capacitance then? The question is, if our initial capacitance is given by this epsilon 0A divided by D, then what is the capacitance of this NIF configuration of our parallel plates with a slab with thickness A in terms of D, A, and the surface area and the charge density, whatever. What is the capacitance? What we can do is, since the metal has a thickness A, we can visualize this configuration as having two capacitors, parallel plate capacitors, which are serially connected to each other. And the distance, if we insert the metal slab just right in the middle point, then the thickness of these capacitances, parallel plate capacitors, will be equal to D minus A divided by 2, because A is the thickness of the slab and D is the total distance between the original plates. So this is the final distance between the plates, D minus A divided by 2. Since in this configuration we have two serially connected capacitors, and we can easily express the capacitance of each capacitors by epsilon 0A divided by D minus A divided by 2. These C1 and C2 are equal to each other and they are serially connected, so the resultant capacitor between these endpoints 1 and 2 can be calculated by the serial addition, and the resultant capacitor will be, if we put these values, epsilon 0A divided by D minus A. So in effect, what we have is, if you put this slab of thickness A in between the plates, then this is as if we are reconfigure the parallel plate capacitor. Everything is the same, but the distance between the plates is equal to D minus A. So, but if in this expression, when you let A goes to 0, then this expression will go to initial capacitance. Okay, so if we decrease the thickness of this metal slab so that it is a very thin metal sheet, we recover the same capacitance. That means this, when you look at this two capacitor configuration, when you insert a very thin metal sheet between the plates, there will be no difference between the capacitance of these two configurations, as long as you keep the distance of these two plates the same. Just you insert a thin metal sheet anywhere in between, making as long as making the slab or metal sheet parallel to the capacitors plates, then there will be no any difference between the capacitances of each configuration. So this is a very important fact, and we will use this fact in solving problems with capacitors having a different dielectric constants in between. Let's think of a capacitor which is initially charged and there is no any connection to nowhere. So suppose we have plus Q charge on the upper plate and the minus Q charge on the lower plate. What we do is an interesting, we keep the distance D is fixed, but the down plate is moved horizontally in, let's say, in the positive x direction, in this direction, a little bit, distance x, let's say. What happens to the capacitance? So what happens to the capacitance is, well, initially we have this uniform electric field between the plates, and if you slowly slide the down plate to the right, for example, then these pair charges, plus and minus charges, want to keep their interactions the same. Okay, for example, if they pair up, if one plus charge is paired up with minus charge, then these pairs will try to keep their interactions fixed or the same. That means when we move the plate, these charges will accumulate only on the overlapping regions. If you look at in the vertical direction, these charges, these pair charges, will accumulate, for example, for the upper plate, so that this region, the overlapping region, will contain all the charges. Okay, when we, of course, slide one of the plates in horizontal direction, there is no any change in the charges because there is no contact. Then the total charge will remain the same. But the thing is, as I said, these pair charges will try to keep their interaction so that they will collect on both the upper plate and the lower plate. They will collect on one region of the plates, and these regions are overlapping region. You see in the initial configuration, all the area for the upper and lower plate overlaps if you look from in the vertical direction. But when, of course, when you slide, this overlapping region will change, and these charges will accumulate only on the overlapping regions. Okay. So let's call the initial area, overlapping area, as A1, or the total area of one of the plates. You can think these plates as a square of size L, and let's A1 is equal to L square. And you move a distance, let's say X, then the overlapping region will reduce itself to L minus X. If you move the lower plate as a distance X, then of course the overlapping region will decrease. So let's call this area of the overlapping regions of both plates as A2. So what happens to the electric field when you keep the distance D is the same? Well, we know that the electric field between oppositely charged plates does not depend on the distance. They only depend on the charge density of one of the plates, and it is just sigma divided by epsilon 0. When we do this sliding, and since the total charge will accumulate on a smaller surface area, okay, we have the same number of charges. The charge will remain fixed, but the charges when you slide will move toward one end. Again, you can say that these plates are in electrostatic equilibrium. Okay, the only thing is that these charges are not distributed evenly for the second case because of the electrostatic attraction between the pair charges on both plates. Okay, but the thing is, the both plates are in electrostatic equilibrium. That means the charges are not moving anywhere. The charges are steady. So as long as the charges are steady on a material, then we can say that this material is in electrostatic equilibrium. All right. So let's call the charge density of the first configuration as sigma 1, and the charge density of the second configuration sigma 2. Of course, when we do this, the sliding, the charge densities on the overlapping regions only will change. For example, the charge density for this configuration will be larger in, of course, only this region, okay, on the overlapping region, because the all charges are now restricted to occupy on a smaller area. That means the charge density is larger. Okay, the total charge again for both configuration is the same. The total charge does not change. And if this is A1 and this is A2, the overlapping regions, area of the overlapping regions, and if A2 is less than A1, then sigma 2 is larger than sigma 1 because the total charge now are restricted on a smaller surface area. And let's call the electric field strength in the first case as E1, and in the second case, the second configuration, as E2. Of course, because the electric field strength only depends on the charge density of one of the surfaces. In the second case, since the charge density increases, electric field strength E2 will be increasing, and E2 will be larger than E1. Now, what about the potential difference between the plates in the second case? Well, since we keep the distance between the plates the same in the second case too, and we know that E2 is larger than E1 in the second case, and since the potential difference between the plates is proportional to the electric field and D, to be more explicit, V is equal to the electric field strength times D. That means the V2 in the second case, the potential difference between the plates, will be larger than V1. So V2 is larger than V1, the potential difference, because the potential difference is proportional to the electric field strength. Now let's think of how the change in the electrostatic energy, electrostatic potential energy of the capacitor changes. Okay, so we know we can express this electrostatic potential energy of a parallel plate capacitor in terms of its charge and the capacitance, and this is 1/2 the total charge on one of the plates, Q square, divided by the capacitance. Or instead of this, we can use the field energy density expression for the potential energy of any region of the space which has electric field, uniform electric field, and this was, remember, just proportional to the square of the strength of the electric field times the volume of the region that this electric field exists. Let's use the second one. Okay, it is just 1/2 epsilon 0 times E1 squared times the volume. Alright, so we can say that in the first case, if the electrostatic potential energy is U1, then U1 is proportional to the E1 squared times A1, because in fact the volume is A1 times D, but since D is not changing in both cases, just omit this D, and we can express this proportional to just concerning E1 and the area A1, because these are changing. So that means since E1 square is proportional to sigma 1 square, which is the charge density over the surface, then this is, in turn, we can express this proportionality sigma 1 square times A1, and of course we can write down the same proportionality for the electrostatic potential energy of the second case, U2. It will be proportional to sigma 2 squared times A2. And so we have two terms in the expressions of electrostatic potential energy, the charge density and A, the area. We can express, for example, for the first case, sigma 1 times sigma 1, A1, but we know that sigma 1 times A1 is nothing but the total charge on one of the plates. So we can express this proportionality, sigma 1 squared times A1, as just sigma 1 times Q. So the expression, the proportionality for the electrostatic energy reduces only to one variable then in that case, because the charge, the total charge is not changing. So this expression has only sigma 1, which is the changing quantity for two configurations. Then we may express these proportionalities as U1 is proportional to sigma 1 times Q, and U2 is proportional to sigma 2 times Q, and Q's are the same for both cases. And the only changing thing is just the surface charge density, and you see the result is immediate now. U2 is proportional to sigma 2 and U1 is proportional to sigma 1. These proportionality constants are the same for both cases. And since sigma 2 is larger than sigma 1, that means the second case, in the second case, the electrostatic potential energy will be larger than the electrostatic potential energy of the first configuration. That means when you slide the bottom plane a distance x, that means you are increasing the electrostatic potential energy. And that means to increase this potential energy, you have to do some work, right? Because you are going from one configuration which has lower energy to another configuration which has larger energy. Just it is, you can see that just moving a object from height which is low to another height which is higher than the first case. You're just increasing the potential energy. And in terms of these energies, it is what we see in here is just the same. We are just increasing the potential energy of the system. So that means you have to do work. Or if you want to slide this lower plate, then you have to pull it. You have to pull it against some force. Okay, I'm not discussing what this force is in nature, but of course you will immediately realize that this force in nature is just electrostatic force between these charges, because you're making these charges closer to each other. And of course, if you want to bring the same charges closer, which are closer to each other, then you have to do some. You have to spend some force on them, right? All right. So we can express this relation between these two potential energy more explicitly as the ratio of the surface charge densities. U2 is equal to the ratio of the surface charge density in the second case divided by sigma, and you have to multiply this the potential energy of the first case. Okay. Well, of course, by that expression you can easily say that if you increase the charge density twice, then you will increase the potential energy twice. That is just, there is a linear relationship. Well, the next question is, then you can ask to yourself, what is the work done to move this plate a distance x, right? And if you move from x0 to some distance x, then of course, since you are overcoming some kind of force, force is electrostatic in nature, then you have to do some work, because you apply a force to move some object at distance x, and the definition of the work is nothing but the work times the distance x. But the thing is here, the work is variable, okay, and well, without considering about the work times the position expression, you can calculate this work just by taking the difference of the potential energy between these two cases. Okay, if you want to calculate the work done by U, then you just take the difference of the potential energy of the second case to the potential energy of the first case. U2 minus U1 will be the amount of work you have to do. But what is U2 in terms of the charge and the capacitance? Well, the capacitance in the second case, since we have a smaller area A2, then this A2, if this distance is x, is just L times L minus x, because plates are square of size side L. Then if you decrease one side by x, that means the area will be equal to not L square but L times L minus x. So you may express the potential energy of the capacitor in terms of its charge and the area and the distance between the plates by this expression, and you will subtract this quantity, which is the initial capacitance of this configuration, which is nothing but 1/2 Q square D divided by epsilon 0 L square. I'm not just mentioning what this expression is. This is, you already know the capacitance, inverse of the capacitance of a parallel plate capacitor. So take this difference, then you have x in the first expression, and this is easy. When you do some algebra, you will see that this work done is 1/2 q square divided by epsilon 0 L square, which is the potential energy of the first configuration, right? Because I think I have done a mistake in here. I have just forgot to multiply the numerator by d, so there must be d in here, right? Then you can see that the first expression, this part, okay, in which there is no term x, this part is nothing but the potential energy of the first configuration, and if you multiply this by this quantity x divided by L minus x, then you find the total work to be done to move the lower plate a distance x. In this example, we have a parallel plate capacitor of the plates in the shape of square and the sides L, and what we do is we slide a dielectric material from the left side a distance x into between the plates, into the region between the plates, and we keep the distance between the plates d as fixed, and you can also assume that the thickness of the dielectric material in this direction is d. So the first question is, when you slide this dielectric into the capacitor, how the capacitance of this parallel plate will change? Well, for this, just fix this distance x and then try to find an equivalent capacitor of this configuration. Well, we already have solved a similar question, that we can always divide this capacitor into two different capacitances. One is filled with a dielectric material which has the same thickness between the plates d, and the other is a capacitor which has no any dielectric between the plates. If this side, the lateral side of the dielectric is x, then on one hand we have a capacitor which has a side of x in this direction and L in the normal direction as the rectangular plates of the capacitor, and it is all filled with this dielectric material K. And in that case, the first capacitor will have the surface area x times L. The second capacitor will be parallelly connected to this one, because the plates, when you divide the plates into two, then you have to connect these plates by a wire in order to keep the plates at constant potential, at the same potential, okay? Because when we divide these plates, you need to keep these plates at the same potential. So that's why this configuration is equivalent to two parallelly connected capacitors. And the second capacitor will have one side L minus x and the other side L, so the surface area is L times L minus x. But this capacitor has no any dielectric between the plates. So the new capacitance, of course, will be the sum of these capacitors, and we may now easily express the capacitances of these capacitors. The first one, since it has a dielectric K, it will be epsilon 0 times A1, which is the surface area of the plate of the capacitor C1, divided by D, and the distance between the plates is all the same for all capacitors, for both capacitors. And the second capacitance has no dielectric, then epsilon 0 A2 divided by D. So if you express these surface areas in terms of the sides L and X, then we have the final expression for the equivalent capacitor. So this is the final expression for the capacitance, which has a partially filled dielectric. The epsilon 0 divided by d L square plus Lx k minus 1. Now, if we keep the potential difference between the plates fixed, or if you connect this capacitor, which is partially filled by dielectrics, to a battery, connecting the capacitor to a battery means fixing the potential difference between the plates. Okay, we can express the total energy of this partially filled capacitance, partially filled with dielectrics, as 1 over 2 CV square. Well, V is constant in here because it is connected to a battery, and C we already get from the previous work, and we can express this energy stored in this capacitor in this configuration. As you see, it is dependent on X, where X is the sliding distance of the dielectric into the between the plates of the capacitor. So next question is, when we change this X, we know now how the energy stored in the capacitor changes, right? Well, we have a potential expression, and it depends on a position of some kind of position, right? It's a function of position. But we know again that all the forces related to the system of capacitor is electrostatic in nature, and we know that the electrostatic forces are conservative forces. That means if we find the energy of the system in terms of some distance, then when we take the position derivative of the energy or potential energy, we get the force that is involved in sliding this dielectric between the plates. Okay. Now imagine you want to try to slide this dielectric in the direction of, let's say this axis is the positive x direction, in the direction of positive x-axis, positive x direction. Then the question is, what force do we need to slide this dielectric into or between the plates? Or will the system pull this dielectric into the region? Okay, let's check this. And we know that the force is just the derivative of this potential with respect to x. Of course, there is a minus sign in the definition, so the force as a vector is equal to minus du or dx in the x direction. Okay, so let's calculate this, whether we must provide the force or the capacitor is pulling the dielectric into itself. So let's do this, and when you calculate this derivative, it's easy because it's linearly dependent on x. We get this expression minus epsilon 0 v squared divided by 2d L times k minus 1. So this expression, these terms are always positive. Epsilon 0 d and v square L, and k is larger than 1 because it's a dielectric. So this expression is always plus, and we have a minus sign here. So the force you see is in the negative x direction. It's minus the unit vector in the x direction. So the force is to the left. That means when you try to push this dielectric into the region, the capacitor will push it back. So you have to provide force to slide this dielectric material between the plates. Okay. In this example, I will derive the electrostatic attraction force between the plates of a parallel plate capacitor by using the fact that the force involved in our system is a conservative force. And for conservative forces, we can use always this principle that the force can be expressed as the position derivative of some potential energy. And to set up our capacitor, we need to spend some energy, and this energy is stored as electrostatic potential energy in the capacitor. And we know how to express this electrostatic energy if you have a constant charge, the charge does not change on the plates of the capacitor, then in that case, from the potential energy of electrostatic potential energy of the capacitor, we will be able to derive the force between the plates. First of all, the capacitance of a parallel plate capacitor with respect to its surface area and the distance between the plates is given by this expression. It is epsilon 0 times A divided by the distance between the plates. I keep the distance between the plates as a variable because the force between the plates will change with respect to this distance between the plates with respect to x. And we know that for a system which has all forces, for all forces of the system, if the forces are conservative forces, then we can express this force as the position derivative of a potential energy. And the potential energy, in our case, is the electrostatic potential energy of our capacitor. And we know how to express this potential energy in terms of the charge and the capacitance of the capacitor. And for a conservative force, this is the general principle that the force is in, let's say, x direction, the derivative of the potential minus derivative of the potential with respect to x. And let's do this for our system. So if you express the potential energy in terms of the charge and the capacitance, because the charge and the capacitance, if you keep the charges are constant, right, and we may express the potential energy in terms of the constant charge times the inverse of the capacitance, but the capacitance changes with the distance between the plates. So we have the potential energy 1/2 q square, the x divided by epsilon 0 times A. And this should be A, okay. So the next is we apply this principle that the force may be expressed in terms of the derivative of the potential energy, and then you can easily find, if you take the derivative of u with respect to x, the distance between the plates, you get the force is equal to minus q squared divided by 2 epsilon 0 A. Well, how can we express, the next question is, how can we express this force in terms of the charge and the electric field between the plates? Well, beforehand, you may claim that if you know the charge inside an electric field E, then it is easy because the force is just equal to charge Q times E. But let's check this. We may always express this electric field between the parallel plate capacitor, and the electric field is the charge divided by the area of the plates, one of the plates, times epsilon 0. So we may express Q divided by A times epsilon 0 as the strength of the electric field. In that case, you will notice that the force is not equal to just Q times E, but 1/2 Q times E as the strength of the force. It is 1/2 Q times the electric field strength between the plates. So we have here we have used the fact that E is equal to Q divided by epsilon 0 times A.